Welcome to lecture 10 of derivative securities. Today's topic is on the Greek letters. So we are also going to talk about how to hedge, like how to reduce risks utilizing the Greek letters. So meaning that Greek letters are actual risk management tools. Before I introduce the tip of the week, let me briefly explain what Greek letters are. So if you look back to lecture 8 and you look into the Black-Scholes model, you'll find that the call prices and the put prices, they are just functions of 5 variables like S0, K, R, sigma square, and time T, actually time to maturity T. So effectively, the Greek letters are just derivatives of the option prices or maybe other financial instrument prices with respect to like the five with respect to those 5 variables. So here let's denote the price of the options as F. Then delta is actually, so now let me expand the tip of the wick. So by starting with expanding what delta neutral and gamma neutral are. So delta is the rate of change of the option prices. So F here just denote that we don't know whether it's call or put. So the like the first order derivative of option prices with respect to the underlying spot price. So that's a delta, and then delta neutral means that this first order derivative is equal to 0. Then for gamma neutrality, gamma it's actually sorry, let me write it as delta is equal to. Then gamma is actually the first order derivative of delta with respect to underlying price again. So if you like expand further, you'll find that this is nothing more than just a second order derivative of F with respect to S, right? So it's the rate of change of delta with respect to underlying price S. So here, like the tip of the wick is saying that delta neutrality provides protection against small price movements, while gamma neutrality provides protection against large price movements between hedge rebalancing. So let me quickly expand like about the meaning of this tip here. So if delta is like if you are able to get your portfolio delta being equal to 0, then for your portfolio, let me still utilize F to represent your portfolio value. So so this delta here, this delta is different from like this delta here, like this delta sign is just representing we are taking difference. So that's it. Like delta F is difference in F. So delta S and delta F and divided by delta S. Approximately if delta S is small enough, since like this derivative is 0, right? If this fraction composed by those difference in F and S, if delta S is small enough, this fraction is also going to be approximately equal to that derivative, and it's going to be equal to 0. Then delta it basically means that delta F is approximately 0. So that's the mathematical expression of the first half of the tip here. So we can see that when delta S is really small, if your portfolio is delta neutral, then like the change in your portfolio value is approximately 0. So that's a delta neutral. And also, if you think about gamma neutrality, so here the second half of the question is saying that gamma neutrality is providing protection against large price moves between hedge rebalancing. So there is actually so let me start by expanding a problem, a disadvantage associated with a delta neutral strategy itself. So for delta neutral, if you don't do any like rebalancing, like if you don't do any rebalancing, if you just like make the portfolio delta neutral at the beginning and then you just leave it, then what happens is that like as time and as the underlying price evolves, your delta, like the portfolio delta is actually going to change as well. If that's the case, what can you do? You obviously you can keep on doing rebalancing, right? So which we are actually going to discuss shortly, but so you can keep on doing rebalancing, but the problem is that the rebalancing would be costly. Like, I mean, if the rebalancing frequency is too high, then the rebalancing is going to be costly. So what you can do is actually also let the portfolio being gamma neutral. So note that gamma is a derivative of delta with respect to S. So if that's equal to 0, so it means that it like the change in delta will be controlled. So even if like if we manage to keep the like if we manage to make the portfolio like gamma neutral, then like even for really large price moves, really large moves in S, actually the change in delta will be limited. So let me write here. So this equal to 0 means even large changes in S like will only need to small changes in delta. That's exactly what we want, right? Since we don't want frequent rebalancing. So once we once we make our portfolio both delta neutral and gamma neutral, then our rebalancing frequency can be lower than the delta neutral only like strategy, since for the first portfolio with gamma neutral as well, the changes in delta won't be that large. Yeah, that's a explanation of the tip of the week here. Now, let me describe the learning objectives. So the learning objectives are that we are going to understand and calculate the Greek letters. So today we're going to discuss 5 Greek letters: delta, gamma, vega, rho, and theta. So for delta, that's just, as I said, that's just a first order derivative with respect to like the underlying price. And for gamma, that's actually just a derivative of delta with respect to S. Then for vega, it's a first order derivative with respect to volatility. And for real, it's a, let me check, I think real is a like a derivative with respect to the interest rate. Interest rate, yeah. Let me just double check. Yeah, so it's just like the first order derivative with respect to r. Now let me go back. Yeah, also to correct my previous discussion, we not only focus on S sigma square and time, we also discuss about R as well. Now let's get back to here. So for Vega, it's as we can tell from its name, as we discussed earlier, it's just a derivative, a first order derivative of the option prices with respect to volatility. And for real, as we just discussed, it's a first order derivative of the option prices with respect to the interest rate R. Then for theta, it's like it's the first order derivative of option prices with respect to the passage of time. So note that here we're not taking a first order derivative of the capitalized T, which representing time to maturity. So here we are actually taking first order derivative with this lower T. Therefore, we are taking like first order derivative with respect to the passage of time. So as time evolves, T is going to be larger, whereas so this small t is going to be larger, whereas so as time passes, I just want to like clarify the difference between smaller t and bigger t. So as time passes, t increases, and the time to maturity, this t, it's going to decrease, right? Now, let's move on to the next learning objective. So, when we are doing risk management, we can utilize the Greek letters. So we can make a portfolio of options, delta neutral, gamma neutral, or vega neutral. So, actually, those strategies can be achieved separately or simultaneously. So the third learning objective is that we are going to discuss the hedging of option positions. So like here, the third objective is just that we are going to discuss specific specific hedging strategies and compare across the four strategies. Yeah, that's pretty much the learning objectives. Now let's move on to the next page. So that's an discussion on that's a discussion on data. So here, like for the above two figures, I'm drawing the total value and intrinsic value of of calls and of puts, right? So those black kinked line are the intrinsic values, and the red, like the red curves, those are the total value, right? So remember that total value is always intrinsic value plus time value. So total value is always like always no smaller than the intrinsic value. Then like we know that the delta is just nothing more than like the first order derivative of option prices with respect to S. Therefore, it's effectively just the slopes, like the slopes of the red curve, the slopes of the total values of calls and puts. Therefore, from this figure, we can actually get the like a feeling about the values of data. So obviously, like for like let's discuss core options first. So for core options, when when the S is really not really S, so not really S0, but like for S smaller t or S0. So if it's really small, then then um then what happens is that like the slope, as we can see from the figure, the slope is really close to zero. So that's so here for the bottom two figures, I'm actually directly drawing data with respect to s. So x axis are s and y axis are data for the below two figures. And if we focus on core again, that slope here I just showed you guys is corresponding to this point. So where delta is equal to 0. And also for S is really large, so far in the money. If that's the case, if it's deeply in the money, then it's approaching like this like positively sloped straight line, right? So and that positive sloped straight line is having a slope of 1. So if it's approaching this line, then the slope will approximately goes to 1 as well, right? So that's corresponding to this point in the figure below. And meaning that the delta will approximately go to 1. Yeah, if the option is deep in the money. We can also get a feeling about the delta at the strike price. So it appears that it should be like approximately 0.5, right? So since it's just like right in the middle of 0 and 1. Also, there's a more intuitive explanation for that value of 0.5. So the intuitive explanation is that the delta of call and delta of put are actually probability, like approximately probability of calls and puts are in the money at maturity. So that like you can approximately view those two deltas as a probability of the corresponding options being in the money at maturity. So for at the strike options, like no matter it's call or put, it get a 50-50 chance of in the money or being out of the money, right? So therefore that probability is supposed to be 0.5 at strike. Let me write it more clearly. Zero point 0.5 at. So this probability would be 0.5 at strike. Then we can also so here basically by discussing this top left figure and bottom left figure, we know that basically for the delta of the call options, it just goes from 0 to 1, so it's positive, and also at the strike it's equal to 0.5. Then we can also like kind of get a feeling about the delta of put options again by looking at its total value, like the slope of its total value. So for put options, we know that if it's deep out of the money, then it should be approaching this negatively sloped line with the slope of -1. Therefore, basically, like when it's deep out of the money, that's the delta. So that's like this slope I just showed you guys, this slope of the total value with respect to S, that slope is corresponding to this point in the bottom right figure. And then let's also take a look at the scenario for the put option where they like when the option is deep out of the money. When it's deep out of the money from the like from the total value of the put options, we know that it's approaching the x-axis. Therefore, that slope is approximately 0. So therefore, like for put options, when it's deep out of the money, meaning that when the stock prices keep, not really stock prices, but like when the underlying prices keeps increasing, then the delta, the slope goes to 0. So therefore, like we get this point here. Also, we can kind of we can kind of work out this 0.5 at a strike basically by thinking that at the strike, the probability of the put are in the money at maturity. Sorry, let me wipe that out. So like for the explanation of this 0.5 here, again, you can just think of delta as probability of the put being in the money at maturity. So if it's at the money, so if it's at a strike, then the probability of being in the money or out of the money is actually just 50-50. So that intuitively explains this 0.5. Of course, for the delta of the put, in order to get probability, you have to take the absolute value. But anyways, it's going to be 0.5, like in terms of the absolute value. Now, now you guys can see that like when you look at call and put, like the delta is actually having the same shape. It's just that for the delta of call, it's ranging from 0 to 1. Whereas for the delta of a put, it's actually ranging from -1 to 0. So one being always positive, the other being always negative. Also, later we will see that gamma, like the first order derivative of delta with respect to S, or you can say the second order derivatives of the price, the second order derivative of F with respect to S, that's actually highest at the strike. So I'll show you guys that later, but like for now, that's the delta. Then here there is more discussion on the properties of delta. So here, the first bullet point is just actually a restatement of what we have just said. So delta is the slope of the curve plotting the option prices against the price of the underlying asset. So those two, which are just say those two top figures we just plotted. So like the slopes of those two figures are the delta. Then, then for the relationship between delta and time to maturity, we have three lines here. Don't worry about this. You can just like get a like intuitive kind of intuitive understanding about this. And don't worry about this. So for like for the blue line, like blue solid line, it's representing like the delta of a call for in the money options. So for in the money options, we know that if the time so like let's think about so we can see that when time to maturity is 0, we have those 1, 0.5, and 0, right? For those three lines, for in the money, out of the money, and at the money. So we can get an intuitive understanding about those three points utilizing the probability arguments I just showed you guys. So for in the money call, recall that delta is probability of being like probability of calls in the money at maturity. If that's the case, if it's representing probability of like the call option remain in the money at maturity, then for in the money options, it's basically a 100% chance to achieve, right? So that's why we like have 1 here for time to maturity equal to the 0. As for this decrease slope for this for in the money call options when time to maturity increases, let me expand this intuition via like total value, actually time value and intrinsic value. So for in the money options, we have time value being increasing if t increases. Like if this capitalized T increases. Yeah, I also wrote here as maturity increases. But note that actually intrinsic value is more sensitive to changes in S, whereas time value is less responsive, less sensitive to changes in S. So if that's the case, if you are having a greater weights on time value, whereas time value is less sensitive than sensitive to changing S, then obviously your sensitivity to S is going to drop, right? Yeah, that's that's a intuition of this downward sloping blue solid line. Then for at the money options, we can see that it's always somehow very close to 0.5, right? So recall that the delta is measuring the probability of the calls remain being in the money at maturity. So as we said, at the money options kind of just have a 50-50 chance to being in the money. Of course, that chance is more that chance of being in the money would be more close, would be closer to 0.5 when the time to maturity is just 0. Now let me also expand kind of the intuition for the out of the money options. So for out of the money options, we can expand this 0 here via the probability arguments. So when time to maturity is equal to 0, recall that the delta is measuring the probability of calls being in the money, like when the option matures. So if that's the case, then since we are dealing with a out of the money options, since we're dealing with OTM, therefore OTM actually barely have any chances of becoming in the money when T is when T is very, very close to 0. So you basically have no chance, right? Since you are very, very far from in the money, maybe even far from at the money. So therefore that probability is equal to 0. And that expands this delta equal to 0 here. Then for out of the money options, it's actually this upward sloping dotted line. Here, for the upwards, for the positive slopes, let me expand the intuition here. So for out of the money options, when maturity increases, you actually, since you have more time, right? So you have more time to fluctuate. Therefore, that more time actually gives you higher probability of turning into in the money options eventually. Therefore that's why you have increased delta, since delta is effectively just probability of turning into ITM. Yep. Actually, here are some of the features we just discussed, actually. So, let me just repeat that one more time. So, delta, this is a implication of delta. So, delta is a relative change in the option price with respect to a small change in the underlying price. That basically means that, so more specifically, this bullet point here means that if S increases by 1, then the value of the call option is going to increase by delta. And the value of absolute value of for the specific example here, we know that the value of the stock increases from 49 to 50.5. And we also know that the delta of an option on the stock is 0.43. So we first calculate the change in S. The change in S is just 1 point. Actually, let me write from the start. So since delta is equal to the the derivative of price with respect to S, right? So it's approximately delta F divided by delta S. If actually, let me write it more clear, to avoid any confusion with the signs. So it's approximately change in F divided by change in S. If that's the case, our change in F for this question is 1.5, right? So like 50.5 minus 49, it's actually equal to 1.5. So that's 1.5. 1.5 divided by actually that's changing S. So changing F is what we don't know. And also we know that delta is equal to delta is equal to what? Let me check. 0.43. So meaning that we can just set this fraction equal to 0.43. Let me equal to 0.43. So if you take this equation, you can solve for changing f, right? So 0.43 times 1.5. And it turns out that if you do the calculation, that's equal to 0.645. So that's a change in your option price. Also, for deep in the money options, actually, I just showed you guys those two bullet points in like the above figures. So for deep in the money options, the delta of the call option is like approaching 1, like very close to 1. And for put, it's approaching -1. And for deep out of the money options, both the like call options and the put options, they are having a delta very, very close to 0. Now onto the data of forward and futures contracts. Here it's showing, so this slide is showing the data of the forward contract. I will show you guys how to derive this, but now let me just walk you guys through like through those formulas. So for data of a forward contract, if the underlying asset is paying continuous compounded dividend yield, then the delta is equal to of that forward contract is equal to e to the power of minus qt. And then for the delta of futures contract, so that's forward contract, right? So for futures contract, of course, if q is equal to 0, then that's just 1. Like since e to the power of 0 is just 1. Then onto the delta of futures contract, the delta is like if it's having continuous compounded dividend yield, then the delta is equal to e to the power of r minus q times t. Also, more specifically, if we're dealing with index futures, for index futures, we know Q is equal to Q. So yeah, we're just using the same formula. And for currency futures, we know that Q is equal to the foreign risk-free rate, right? So Q would be equal to RF. Sorry about that. And then for like the silver futures, we know that it's not paying any dividend yield, therefore Q would be equal to 0. So those three, like index futures, currency futures, silver futures, those are just 3 application examples of like this third bullet point here. like of this delta of the futures. Now let me derive the delta of forwards and delta of futures respectively. So here, for forward contracts data, we are just deriving it based on the like the value of the contract. Remember that previously we are using this small ft like to derive to denote the value of the forward contract, right? So we know that this value of the forward contract ft is equal to capitalized f t minus k, and then close bracket times e to the power of minus rt. So that's a value of a forward contract. So we are like discounting it back by timing e, like discounting it back to like to the current point, to t, basically by timing e to the power of minus rt. So here this is like this ft minus k. Yeah, this ft minus k, that's actually like so yeah, back to that ft minus k. So for ft minus k, it's like, remember, if you guys still remember, that's representing the payoff of closing out early, but you are receiving like, so you are closing out by entering into like an position with the opposite direction. But like, but even if you are like closing out your position, entering into an opposite transaction, like you are still like receiving those payoffs ft minus k actually at maturity. So here ft, that's the current forward price of the underlying asset as times small t, whereas k is actually like the agreed upon prices set at the beginning of the forward contract. Yep, that's like that's a ft minus k here, and we have to discount it back for the for the forwards, since it's like ft minus k is realized at maturity. Then we actually also know that this is also from previous sessions, like ft is equal to st times e to the power of r minus qt. Here, if we plug the second equation into the first equation, like if we just replace ft with this st times e to the power of r minus qt, then we'll get that the ft is actually equal to this, like st times e to the power of minus qt, subtracting k times e to the power of minus rt. Then to get the delta of the forward contract, we just take first order derivative with respect to st. And we notice that actually only the first term, like st times e to the power of minus qt, contains st. And once we take derivative with respect to st, we are only left with e to the power of minus qt. Then for futures data, recall that futures is characterized by like continuously marking to market. So meaning that from day to day, you will be receiving some cash or paying out some cash on your account. So like the value of the futures contract is going to be reset to 0 after closing the market every day. So if that's the case, then the value of the futures contract is not discounted because it's actually just realized um, like every day immediately. So therefore, we don't do any discounting for this FT minus K. Then we can again substitute. So here we have this FT, smaller FT is equal to bigger, like capitalized FT minus K, right? So if we again substitute the second equation, the equation, like the relationship between FT and ST, back into this value, we'll get that FT, like small FT is equal to ST times e to the power of R minus QT, and then subtract K. And again, only the first term contains ST. So if we take first order derivative with respect to ST, then we'll get that delta is actually equal to e to the power of R minus Q times T. So yeah, that's how we derive those deltas. Then so that's like the delta of forward and futures. Then for delta of options, it's determined by um these equations. So we kind of already like look at the formulas at the beginning, but for those formulas we discussed in the beginning, actually that's delta of European calls and puts on non-dividend paying assets. Therefore, the delta of call is for the underlying asset with no dividend paying, the delta of call is equal to ND1 and delta of put is equal to ND1 minus 1. But then for like the options with continuously compounded dividend yield Q, we have an extra term here for the delta of call. So instead of ND1, now we times e to the power of minus QT to reflect the impact of dividend yield. The same applies for put. So compared to the version without dividend yield, now the delta of put, instead of being ND1 minus 1, it's now actually ND1 minus 1 times e to the power of minus QT. Also, like the D1 is changed as well. Like recall that for we discussed in lecture 9, the D1 is going to be equal to like this with an extra Q here. Like we're subtracting an extra Q here. Before I move on to theta, let me quickly give you guys an example of delta neutral strategy to show you guys why we are using like kind of to give you guys an intuition of why we are using the Greek letters as a risk management tools. So here we like in this specific example, we may be longing delta 0 of the spot. So the like this delta 0 here, that's actually sorry, it's not delta 0, it's actually delta O. So we are longing delta O of spot, and that delta O is actually the delta of the option. So here we are shorting one call option. Let me just write it here. So on the one hand, we are shorting one call option. So like the unit of the call is one. And we already know that its delta is equal to delta O. Therefore, we can try to make our portfolio delta being equal to 0, right? And what we do to achieve that 0 delta is actually we also long delta O of spot. Did I discuss the delta of the spot? Let me just check. Anyways, let me just quickly derive the delta of the spot here. So delta of the spot would be the first order derivative of S with respect to S, right? That's just one. Yeah, let's not write that out to avoid confusion. So anyways, like the delta of the spot is just one. And we are longing delta O of that spot. Therefore, the corresponding delta associated with spot positions will just be equal to delta O times one. Therefore the return associated with that, not return, the delta associated with that position is delta zero, delta O. And then for the delta associated with shorting one call would actually be our position, which is -1 since we are shorting. So again, our position times the delta of option. So -1 times delta O. Recall that the delta of the call option is expressed as delta O. So basically for that short position, the delta associated would be minus delta O. And for the portfolio delta, of the positions in the spot and the positions in the option, would be adding up to 0. So that's a quick example of a delta neutral strategy. So but the problem is that delta actually changes through time, as the spot ST changes. So this 0 we just obtained now may actually not, it's actually highly likely that it's not going to hold in the future. So delta may not equal to 0 anymore in the future when ST changes. Then yeah, I also write the mathematical expression here. So once time goes by, once ST changes, now the portfolio delta will actually become delta O. So minus delta T. So delta O is just the delta associated with the non-position in the spot, which is remain the same throughout time. But for for the delta associated with the short position in the option, it's actually minus one times delta T. That delta T is changing throughout time. So it will change from delta 0 to some other value. If delta T is not equal to delta 0, then the portfolio delta will not be 0. And we are trying to utilize delta neutral strategies to protect our portfolio against small price movements, right? So basically the core, if we're implementing a delta neutral strategy, what we want to achieve is just that we want to keep delta equal to 0 all the time. And then to achieve that, we just need to rebalance the portfolio from time to time. So here for this specific example, if the option delta does changes into delta t, then like for this specific example, we just need to change the number of shares of the spot from delta 0 to delta t. But like even if you do that, if you implement that change in the positions of the spot, but as time goes by more, like the delta of the option is still going to change, right? So you have to keep on doing that, keep on basically reverting the delta back to 0 by changing the positions in the spot. That's what we call as rebalancing. Then we also have now basically that's the end of delta for now. Then we also have another Greek called as theta. So theta is the rate of change of the option price f with respect to time t. So it's a first order derivative with respect to t, as we discussed earlier. One feature with theta is that it's no greater than 1. So it's smaller than or equal, actually no greater than 0. So it's smaller than or equal to 0. It can be derived via this, via total value is equal to intrinsic value plus time value. Since f is equal to intrinsic value plus time value, therefore the first order derivative of f with respect to t can just be writing as the sum of the first order derivative of intrinsic value with respect to t and the first order derivative of time value with respect to t. Since the first term, like the first derivative, intrinsic value against t, that's actually equal to 0. And the first order derivative of time value with respect to this smaller t is actually smaller than 0. So t here, it's representing the passage of time. It's not representing the maturity left. Therefore, as time goes by, the remaining time value actually reduced, right? So that's why we have this second term being smaller than 0. Since the first term is equal to 0 and the second term is smaller than 0, therefore the theta intuitively is no greater than 0. Also, I know this is a mess here, like the computation of this is not required, so don't worry about that. So that's the setup of a European call. And this bullet point is just saying what we just said, like we just discussed, like the theta is usually negative. Because as time evolves, the time like the time value actually drops. It's actually more important to kind of understand the implication of theta. So the implication is that let me change my pen. So the implication is more important for all the Greeks. And the implication for theta is that theta is a rate of change of the option price with respect to time t. So basically, if your time increases by 1 unit, t increase by 1 unit, t increase by 1 unit will lead to the option value decrease by theta. Yep, that's that's the kind of mathematical expression for this implication. Yeah, also we have a specific example here. for this specific example, we know that the theta is minus it's minus 4.31 per annum. Therefore, to convert it into daily, we have to divide by the number of trading days in a year, 252, and we'll get that the theta the daily theta being minus 0.0171, and the economic implication behind this value is that the value of the option is going to decrease by 0.0171 per trading day. So that's like kind of an application of the implication in the first bullet point. Then move on to the next page. So that's just give you guys a like overview feeling about like how theta is going to change with respect to sorry about having no y-axis and x-axis here on this figure. So for the y-axis, that's actually just theta, and on the x-axis, that's just s. So it's showing how the theta is changing, like when the underlying prices changes. So for out of the money options, the theta is so for this figure, actually theta is most negative at the strike, so somewhere near here, right? And also it's less negative for out of the money options. So we can basically say that like the option price is most sensitive to like to any change in T at the strike price. Like it's actually majorly because, let me just write the reason here for being most sensitive at strike. So the reason is just that the at the money options compared to out of the money and in the money, compared to those alternatives, actually at the money options, they have most time value. So that's a major reason why. So like time value is just a measurement for basically for uncertainty in the future. So since at the money options, it's actually having the highest uncertainty, therefore it's having the highest time value. And since time value is definitely more responsive to T, right? Compared to the intrinsic value. So therefore, for at the money options, it's having the most time value, so it's most sensitive to T. Then for gamma, so we kind of already discussed like something about gamma. So gamma is just a rate of change of delta with respect to price S of the underlying asset, meaning that it's actually a second order derivative of F with respect to S. Also, the gamma of European call and put options, it's calculated like this, but don't worry about that. Computation of this formula is also not required. So as I said, for Greek letters, it's more important for you guys to understand the implications, like the first bullet point here. The first bullet point here, that's the implication. And you have to like know how to apply that implication. So let's take a look at the specific example here. So for this specific, also that's also something about this implication. So if S increases by 1, then the delta changes by gamma. So that's the implication. And then for the specific examples, for this option with those features, where the gamma is equal to 0.066 and delta equal to 0.5216, now we assume that the value of the stock increases, that's actually the same as previous, so it increased by 1.5. And then what's the change in delta? Recall that it's measuring the rate of change of delta with respect to S, right? So meaning that it essentially just means that it just means that delta sorry, change in delta. Let me just use words to describe. Change in delta is equal to gamma times change in S. So here we already know changing S is 1.5. We also know the gamma is equal to 0.066. So we can calculate the change in delta accordingly. It's also like written here. That's going to be 0.066 times 1.5. That's equal to 0.099. And the delta will now change from 0.516 to 0.6206. So you just add for the original delta, you just add the change. Then you get this new delta. Then like for the properties of gamma, so we kind of said that gamma is actually most sensitive at the strike, right? So here, this figure is describing, like on the y-axis, that's the gamma. And on the x-axis, that's S. So from this figure, we can see that gamma is peaking at the strike, like in the middle. Also, like the gamma can be reflected like by plotting the x-axis against S, but the y-axis as delta, then gamma would be like just the slopes on the curve. So we can see that like both from the top figure and the bottom figure, one is plotting delta against S, the other is plotting gamma against S. Like from both, we can see that actually gamma is approximately 0, since those slopes are approximately 0 when the options are deep out of the money and deep in the money. And aside from that, also like the slope of this first figure is the steepest, like it is the highest, like the slope is the highest when like when we are like at the strike. So that's also reflecting gamma is highest at the strike. Now, here, we have relationship between gamma and time to maturity. So don't worry too much about the figure here. Um, all you really need to understand is actually just this like red solid line. So here we have three lines. One like the green line for the out of the money options, and the red line for at the money options, and the blue line for in the money options. So here, for the red line, it's interesting in the sense that when t like when the time to maturity, the capitalized T approaching zero, the gamma is getting higher and higher, right? So, how can we get the intuition of that? Like why the gamma is becoming higher and higher when the maturity is reducing? So we can kind of get the intuition from the from the total value curve and the intrinsic value curve. So recall that. So here, the red line, um, maybe for example, let's assume that the red line is representing the total value at current time. So this is the total value at current time. And the blue line is the intrinsic value. And then as t approaching zero, what happens is that the total value is approaching the intrinsic value, right? So let's say since it's approaching the intrinsic value, maybe the blue line is the total value after after maturity reduces, and we can clearly see that the curvature like at the curvature at the stripe sorry, the curvature of the blue line is significantly larger than the red line, right? And recall that gamma is actually representing curvature of the price curve. So since like this derivative, this second order derivative, that's actually curvature. Curvature. So that's A. Oh, not A. That's actually U. Sorry. So that's U. So the second letter here is U. So that's curvature of F. And we can see that the blue line is obviously having a greater curvature, right? So like here, basically what I'm trying to say is that like the phenomenon we observed here is that as time to maturity approaches zero, the peak in the figure, like in the above figure, the peak here is getting higher and higher. Since this is for at the money option, right? So and that's actually reflecting it means that the peak at the strike is getting higher and higher since we're dealing with at the money options. And also if we like for this phenomenon, the reason behind that is that if we draw the figures of total value and intrinsic value, we know that when t is equal to zero, total value is approaching the intrinsic value, meaning that the curvature at the strike price, like the curvature here and the curvature here, is increasing, like it's increasing from the red curve to the blue curve. Like it's increasing when t decreases. So if gamma is small, recall that gamma is just the rate of change of delta with respect to changes in the underlying price, right? So if gamma is small, then it's good. It means that the delta changes slowly with respect to changes in the underlying. And therefore, we only need infrequent portfolio rebalancing for delta neutrality. But if gamma is too large, then delta is very sensitive to any change in S. So it's actually very risky to leave the portfolio unchanged for too long, because if you leave that portfolio like with large gamma for like unchanged for too long, then your delta must have changed already. Therefore, like you basically just lost that delta neutrality, right? And your portfolio value is going to vary a lot as well. So here, this table, it's a summarization, like of the signs of the calls and puts. So note that, like when you are taking short positions, like no matter calls or puts, the signs are just the opposite of the first two rows, like of the corresponding long options. And for the long, for the long positions, if you long a call, the delta is always positive. So like obviously, like if you long a call, you are going to have increase in the value if they if increasing the option value if the underlying price increases, right? And also for gamma, like so sorry, for delta of longing a put, that's going to decrease with underlying price. It's also intuitive because for put, you expect to profit when the price drops. So meaning that the value of your put is going to increase when the underlying price drops. So a negative sign for the delta. Then for gamma, so for gamma, like for both calls and like for both long in call and long in puts, gamma is always positive. So it's always this positive sloped bell-shaped curve if you draw gamma with respect to S. As for theta, so for theta, um, actually for both calls and puts, I just showed you guys that that's actually a negative sign, right? So since for theta, you are taking like first order derivative with respect to intrinsic value and time value and adding them to sorry, you are taking first order derivative of intrinsic value and time value with respect to t, and you are adding those two derivatives together, whereas the first derivative is equal to 0, and the second derivative is smaller than 0. Therefore, for theta, the sign, like regardless of calls or puts, it's always negative, since as time goes by, the time value decays for both calls and puts. Now, actually we have some extra formula here on the like on actually on the tip of the lecture. So it's like delta, like this sign here, it's actually representing the change in portfolio value. So for a delta neutral strategy, a delta neutral portfolio, the change in portfolio value is approximately equal to theta times delta t plus 0.5 times gamma times delta s squared. So this I know that I kind of already expand about the tip at the beginning, but this equation also helps expanding about the tip. So if you guys pay attention to here, you can see that for delta neutral portfolio, delta s squared is only like appearing together with gamma, right? So if the delta s squared is small, it means that you have small price fluctuations of spot. So it's just small fluctuations, right? Like small price movements. So it's like the delta S square is approaching zero, reflecting small price movements. If that's the case, actually the change in portfolio value will just be approximately equal to theta times delta t. So um, that's actually good. So means that our delta neutral portfolio is successful. But if we have large price fluctuations, right. Uh, Large price fluctuations means you have uh large price fluctuations of spot. So large price fluctuations of spot will mean that delta S square is high. So you basically can see that if like for high price movements, like if your portfolio is delta neutral only, if gamma is not equal to zero, then actually your portfolio value will still be will still be influenced by large price fluctuations. So although it's not influenced by small price fluctuations. So if it's not impacted by delta S square if delta S is small and gamma is not equal to zero. But if but gamma not equal to zero means that your portfolio value will still be impacted by large delta S square, by large price movements. Yeah, that kind of like this formula here kind of also helps expand like the tip of the wick. One more thing is that you guys can also like work out those two bullet so you guys can also work out those two bullet points. by looking at the like the signs table here, by figuring out what's the sign for the first term and what's the sign of the second term. Yep. So I will leave that to you guys. I will no longer dwelling on that. Now onto Vega. So Vega is the rate of change of the option with respect to the volatility. So again, it's a first order derivative. It's the first order derivative of F with respect to sigma, the standard deviation. So for Vega, its implication is that if sigma increases by 1%, if the standard deviation increases by 1%, then the option value increases by 0.01 times V, times V stands for Vega. And also in this figure below, I'm showing you guys a relation between Vega and the underlying price. So again, Vega is actually most sensitive at the strike. So as we described earlier, for let me check. For theta, so here, so for theta, we already said that actually theta is also highest. Sorry, actually theta is most negative at the strike because at the money options have most time value. So the same logic applies here. So for the now for Vega, when at the strike, since at the money options they are having the most time value, therefore, time value, it's actually more sensitive to changes in volatility, whereas the intrinsic value, it's not that much impacted by sigma at all. So here Vega is highest at the strike merely because most of the time value is there, and also time value is most sensitive to the volatility changes. Then onto real. So for real, it's the rate of change of the option with respect to the interest rate. And its implication is that if R increases by 1%, then the option value increases by 0.01 times real. So note that Vega and real is a bit special because we usually quote standard deviation and the interest rate in terms of percentage, right? So therefore, the implication is that any 1% change in sigma or 1% change in R is going to lead to 0.01 times Vega or times real times real units of changes in the option price. Also, for currency options, since we have two interest rates, so one domestic rate and the other the other rate being the foreign rate, therefore we actually have two rails corresponding to each of the rates. Then we're just going to utilize delta, gamma, and Vega as risk management tools. So effectively by setting all of them or some of them equal to 0, So delta neutral, gamma neutral, or vega neutral. Here, the first bullet point is just saying that Greg's, like the calculation of Greg's over portfolio. So delta, here it's actually showing the calculation of delta over portfolio. So we kind of already did this before, but more formally, delta for the portfolio delta P is equal to weighted average of delta of each of each asset in the portfolio. So it's WI times delta I, and we are summing up from I equal to 1 to so we're just summing up delta for individual assets. We're just calculating the weighted average of delta for individual assets in order to get the delta for the portfolio. So also, as I discussed earlier, Greeks quantify risks, so therefore Greeks can actually be used as risk management tools. So that's this section here all about. Now, let me specifically discuss about the delta hedging or delta neutrality. So to do delta neutrality, we just let delta P equal to 0. So we are just we can hedge options with different assets. So we can hedge the options with underlying asset, or we can hedge the options with futures contracts, or we can I actually wrote it here, but it's a bit unclear, but let me zoom in. So since delta neutral just means that delta P is equal to 0, so we can just utilize different types of assets to hedge our option to ensure that delta P is equal to 0 if we combine the option with that asset. And the alternative assets we can use to hedge options include underlying asset, futures contracts, and other options. So here, I'm showing basically that so WA is just say the positions you need to use if you hedge the option utilizing the underlying asset, then NWF is actually the position in futures if you choose to hedge the options with futures. So actually those two positions, they are having this relationship. So WF is equal to E to the power of minus R minus Q close bracket times T, and then times WA. So it's just expressing the relationship between WF and WA. So whereas WF is a position in futures if you use futures to hedge options, and WA is a position in underlying asset if you use underlying asset to hedge the options. Let me show you guys how did we derive that. I know it looks a bit confusing here, but let me show you guys the derivation and it will become clear. So I also wrote it here. Recall that we can hedge the options with those three alternative options, right? And recall that delta of the spot is just equal to 1. Since we're just taking first order derivative of s with respect to s, and since gamma s is derivative of delta s against s, like the derivative of a constant is going to be equal to 0, right? And for vega of the underlying asset, it's equal to like again the derivative of 1 with respect to sigma. So again, it's a derivative for a constant, therefore it's again equal to 0. Then for futures contracts, we know that like from previous derivation, we already showed that delta F is equal to E times R minus Q, close bracket, times T. Sorry, E to the power of R minus Q, close bracket, times T. That's from previous calculation. And for gamma, like for gamma of futures contracts, that's actually again 0. So if you take first order derivative with respect to s for this delta f, you'll get 0 as well. Also, the vega of futures contracts. The vega of futures contracts, it can be calculated basically by utilizing like the futures value, this ft. You take derivative of like with respect to sigma. So if you try it out yourself, you'll find out that vega of futures contract equal to 0 as well. Whereas where this ft stands for the value of the futures contract. So we get the deltas we want. Let me show you guys how to what are the WA and WF based on those deltas. Actually, like the notation I use here is a bit different from this equation. So I actually denoted the position in the underlying asset as WS. So just bear in mind that WS are just WA. So basically I calculated for WS and WA, but before that, let's look at the vegas. So if you look at the gamma and vegas for underlying asset and futures contracts, they all equal to 0, right? Therefore, it means that we cannot, if we want to make the portfolio being gamma neutral or vega neutral, we cannot only use underlying asset or futures contracts since they just have 0 gamma and 0 vegas. And in that scenario, like that's actually the last bullet point here. So in that scenario, you have to like in order to achieve gamma neutral or vega neutral, you have to take positions in other traded options. Because for other traded options, they have non-negative gamma and non-negative vega. Now, let me get back to the second bullet point and help you guys derive this equation here. So based on the data we derived, if we want to create a delta neutral portfolio utilizing the option together with the underlying asset, then we have WC times delta C. So the WC stands for the position in the call, plus WS times delta S is equal to 0. So WS stands for the weight in the underlying. Here we just we just assume that we short one call. So therefore WC is equal to -1. Then we already know that delta S is equal to 1, right? So delta S is equal to 1. Therefore, in the scenario, if we only short one call, we can easily derive that WS is equal to delta C. So that's the delta for the call option. So basically WS is equal to delta C if we short one, if we only short one call. Sorry about my awful handwriting here. So that bear in mind that that only holds if we short only one call. It's just purely for the derivation of like the equation in the second bullet point. So also under the assumption of shorting only one call, we can write out like if we hedge with futures, we have WC times delta C plus WF times delta F is equal to 0. And we just assume delta C is equal to -1, right? We're just shorting one call. And we already know that delta F is equal to E times R, E to the power of open bracket, R minus Q close bracket times T. So like based on that, we know like we can now solve for delta F. And if we solve for delta F, we can get that WF, the position in the futures, is equal to delta C times E to the power of minus open bracket R minus Q close bracket times T. So if you compare the above equation with the equation below, that's exactly the formula like in the second. So if you combine those two, effectively that's just a formula here in the second bullet point. Now that's specific examples of like delta hedging, gamma hedging, and vega hedging. So for this first example, we are achieving two neutrality at the same time. So we are achieving delta and gamma hedging at the same time. We know that the financial institution has a portfolio of OTC options on dollars with delta equal to minus 450, and also the gamma equal to minus 6,000. Also for a traded option, it's having delta 1 equal to 0.6 and gamma 1 equal to 1.5. So the question is asking that what position should we take in this traded option here, like the traded option. like what option we should, what position we should take in this traded option in order to make our original portfolio of options being delta neutral and gamma neutral. So here we can just list out two equations. Oh, sorry, I forgot to mention that. So this is OTC options on dollars. So these are actually just currency options. So we're not only achieve the hedging utilizing traded option, we're also hedging by taking position in the underlying asset. And that underlying asset are dollars, currency options. Yeah. And our underlying are dollars. So like whenever you are asked to achieve two neutrality, like gamma neutral, delta neutral, or delta neutral and vega neutral at the same time. So like as long as you are required to achieve two neutrality, you actually have to involve two instruments. So if you like, obviously, if you only have one known but two equations, you cannot solve for a solution, right? So that's a reason, like that's a whole reason why you need to have two financial instruments because you have two equations to solve. If you like, only if you have two, like only if you have more than two instruments, you can get solutions to that two equations, right? So here we just let the like we just let this portfolio delta and portfolio gamma equal to 0. So we're just calculating like it's actually not the like for my previous expression, it's actually not weighted average. It's actually just the delta times predation. So it's not, sorry about that. It's not weighted average. It's delta times predation. And then adding up together. So for each of individual asset, you calculate its delta by timing its position with like delta of each unit, and then you actually add those products together. So now back to the specific example. Here, we calculate the portfolio delta to be equal, like the portfolio delta, like after the delta hedging to be equal to delta, which was the original portfolio delta, and then plus basically the delta from the traded option. So if we denote the like the position in the traded option as W, then that's just W times delta 1. And then if we denote that position, so it's already here, so I'm not rewriting here, but let me just like expand those W and WS in words. So W is position in traded option. And WS like just position in spot. So if you use position in spot times delta of spot, then you basically get like you basically get the like the delta associated with those positions in the spot, right? And if you add them together, you get the you just get the like the delta of the portfolio, and the gamma of the portfolio is calculated the same way, and then we just set the delta of the portfolio and the gamma of the portfolio after the hedging being equal to 0. Now we just need to like substitute numbers into those two equations. So gamma is equal to minus 6,000. So that's the gamma of the original portfolio before hedging. And then you plus W times gamma 1, like of the traded option, that's 1.5. So that's 1.5 here. Then for gamma S, like we already know that gamma S equal to 0, right? So that's what we previously derived. Now we successfully get the equation about gamma. And then for delta neutral, delta, the original delta without any hedging is equal to minus 450. And then when we are hedging with the other traded options, we just use W, the position in that other traded option, times delta 1, which is 0.6. And then you plus WS, that's the position in the spot, and then which is timed by 1, which is that 1 is delta of spot. And then you just like let that portfolio delta being equal to 0. And then we just have like a equation system with two unknowns, like W and WS, right? And also two equations. So we can easily solve for W and WS. And W is equal to 4,000 and WS is equal to minus 1,950. So the answer to this question is that we are going to take a long position in 4,000 traded options. And also we are going to take a short position in minus 1,950 dollars. So yep, that's W and WS we get. So I'm going to leave this example to you guys. So this is an example of achieving delta, gamma, and vega hedging all at the same time. So here we are hedging a portfolio of options again. And now we have two traded, also we are still dealing with the currency option. And now since we are trying to achieve like 3 neutrality, meaning that we have 3 equations, therefore we need 3 instruments, right? Here we have 2 traded options. And also, of course, since it's a currency option, we can like utilize the spot, which is the currency, which are the dollars. So that's the 3 instruments we are going to use to create like 3 equations. So I will leave this to you guys. Also, by the way, like we wouldn't be asking like 3 neutrality at the same time, but we could ask for any of the 2. So because like all the 3 is actually just too complicated, but any combination of 2 neutrality might be tested. So in practice, the traders usually ensure that their portfolios are delta neutral at least once a day. So also aside from delta, whenever the opportunity arises, they are also trying to improve gamma and vega as well. So whenever the opportunity arises means that whenever the hedging cost is low. But they are changing the delta most frequently. So they are like trying to achieve delta neutral most frequently. Also, like in reality, as the portfolio becomes larger, hedging actually becomes less expensive. Now, our final section today. So here, what we are trying to achieve is that we are going to hedge a European call option on 100,000 shares of non-dividend paying stock. So also the value of our European call option is actually 300, like the market value of this European call option is actually $300,000. Now, the extra information we know is that the theoretical Black-Scholes option price is $240,000. So theoretically, since we are shorting a call, like selling a call for a higher than theoretical price, therefore, theoretically, we are earning the difference, right? Since we are buy low and sell high, therefore, we are earning the difference of 300,000 minus 240,000. And that's actually, sorry, I'm missing 10 here. So that's actually $60,000 of theoretical profit. But how can this financial institution lock in this profit? Meaning that locking this profit by basically means that how does a financial institution hedge its risks. So for the following slides, we discussed several alternatives. So we may go with a naked position, we may go with a cover position. We can also adopt a stop loss strategy, or we can do dynamic delta hedging. Let me discuss them one by one. So for the naked position, so if we do not do any hedging at all, like from previous lectures, we know that they pay, like the profit and losses function will be something like this, right? So that's a profit or losses from shorting shorting call options. Also, from this profit or losses function, we can see that we actually have unlimited losses for naked short call. Then like if we actually here we have like a specific scenario where ST rises to 60. So we did the calculation associated with that. So the payoff would be K minus ST times 100,000 shares. And you also plus a call premium. So since you are shorting the call, so you are receiving the call premium, right? So for the first term, the payoff, that's 50, which is the strike price, right? So if you go back, you can see that 650 is the strike price minus 60, the stock price we assumed, like the current, not the spot price at maturity, we assume it to be 60. So 50 minus 60, also timing the number of shares associated with our option portfolio, which is 100,000 shares. That's actually minus 1,000K. So if you add that minus 1,000K with 300K, you'll get minus 700K. Then onto covered position. Obviously, like the naked position is not good, not optimal, right? So since our risk is actually very large, since we have unlimited losses, then what about a covered position? Actually, we are covering this call, this short position in call, by buying 100,000 shares. So we're just generating a covered call by utilizing the underlying asset, by longing the underlying asset. Also, if you guys recall from the previous lectures, covered call is actually just going to have a profit and losses which is similar to like the shape of profit and losses of shorting a put. Also, for this question here, like the covered call will be this red curve. So it's nothing more than just like this kinked curve. That's a profit or losses from shorting the call, adding up together with this blue line, like the profit and losses from longing the stock. So those two curves adding together will be equal to the covered call, like this red line. And that shape is resembling shorting a put. But actually for shorting a quote, though we are able to successfully eliminate unlimited losses, but as a cost, we actually generate losses when the spot price are low. So this is not desirable as well, like the losses when spot price is low. And then for the for this third bullet point, we're just showing a specific scenario where we are generating losses when spot price is low. So here, like the spot price at maturity is assumed to be 40. Therefore, the profit and losses would be calculated as ST minus S0 close bracket times a number of shares and then plus call premium. So remember that we're shorting a call, and also when the stock price is lower than the strike, so 40 is smaller than 50, simply we don't have execution of the option. So the first term is merely the the profit or losses from the from the spot, and also for the call options. So it's not exercised, but for the second term, we still receive some premium on it. So therefore, for the first term, for the profit and losses associated with spot, we just use 40 minus 49. So 49 is like the spot price at beginning. So 40 minus 49. And you times the number of shares, which is 100,000. And if you do all the calculation and you add the call premium as well, you'll get that profit and losses associated with this strategy when ST is equal to 40 is minus 600,000. So it's still large, right? So we are still generating large losses when spot price is low. So this strategy is not that desirable as well. Also, recall that for shorting the call, we actually expect to get profit when the price is low. But now we are even achieving losses when the price are extremely low. So like we kind of already failed at our purpose, right? So our purpose is to get profit when the underlying price is low, but now actually we're generating like for some of the times for the extremely low spot prices, we're actually generating losses for this covered position. So it's not desirable as well, even though we eliminated the unlimited, like the possibility of unlimited losses. Then we also have stop loss strategy. So here, this stop loss strategy can be, let me just expand this via this figure here. So on the y-axis, we have ST. On the x-axis, we have the passage of time. So as we can see, as time evolves, the like the underlying price may decrease and increase and decrease and increase. So it's fluctuating throughout time, right? So for stop loss strategy, its implication is just that we are going to buy the underlying as soon as price exceeds the strike price. And also we're going to sell the underlying as soon as price fall below the strike. Therefore, as we can see here, so here I'm actually like this is actually 50, the strike in our question. So once like for example here, once this price go beyond that 50, actually we're going to like for the stop loss strategy, we're going to buy the underlying. We're going to buy 100,000 shares, and then if you go like if time still continuous evolving, and then we go to this point instead, and now this point is like it's falling below 50, right? So therefore, at this point, we're going to sell the underlying, sell the shares. So you can kind of get an intuition of what this strategy is trying to achieve by looking at the covered position here. So for the covered position, we can see that we are only like longing the underlying as soon as the price fall. Sorry, actually here we are longing the asset. Oh, sorry, longing the underlying always, right? So if you forget about the left hand side, so if you just ignore the left hand side, actually on the right hand side, what we are doing is that we are like buying the underlying as soon as the price exceeds 50. So we basically will be able to achieve this right hand side here, like of the red curve. And then also for the left hand side to the strike price, like when the spot price are lower than 50, we are actually shorting, like we are shorting the underlying. So for that scenario, now it will just improve this curve, right? Like you guys can see that for this curve, we are generating losses for extremely low like spot prices. But if for this section, like for this interval, if we are shorting the underlying, actually we're going to earn positive profits anyways, because like when stock price decreases, both your short position in the core and short position in the underlying are going to like get profit, right? Get positive profit. So yeah, that's an intuition of this stop loss strategy. But actually this stop loss strategy doesn't work well because the cash flows at different points in time must be discounted. And partly due to that, and also because of other reasons, like the purchases and sales cannot be made at the exact price of $50. So ideally, like for this strategy, when we are buying or selling the underlying to hedge, we want the price to be the strike price. But actually in reality, most of the cases, since we are buying when the price are rising, therefore we actually tend to buy at a price higher than 50. And also we are going to sell since like we are sell with a downward price trend, right? So usually we are selling lower than 50. Actually that buying higher than 50 and selling lower than 50 are going to incur losses for us. So that's why this stop loss strategy is not that optimal. Then our final like final agenda today, dynamic hedging. For dynamic hedging, like dynamic delta hedging, um, so the idea is just that the option delta is a function of time and the stock price, so which we discussed earlier. Therefore, it changes over time. So the dynamic delta hedging is just that you have to like rebalance rebalance the portfolio to make delta being equal to zero again. So like dynamic delta hedging just refers to the process of maintaining a delta neutral portfolio throughout time via rebalancing. Here, those two slides are actually on the Excel file. So now let me show you guys the Excel file. So basically those two slides are showing that if we create like a dynamic hedging strategy, actually our cost of um, um, like our hedging cost, like the cost of hedging the option will just be approximately equal to the Black-Scholes value of the corresponding option that we want to hedge. So for example, if we are shorting a call, then if we are doing this dynamic hedging, then the Excel file is just going to show you guys that actually the hedging cost we incur is just the value of that like the value of that short position in the call. Therefore, that being said, like with this first bullet point, therefore this dynamic hedge portfolio is actually just composed of that short position, like that short position in the call. And also, since like as I said earlier, the hedging cost is already equal to the value, therefore our hedge like the instruments we use to hedge actually forms a synthetic long position in the option. So yeah, so actually all the Excel files are just trying to say that our dynamic hedge portfolio is just our original short position in the call and also a synthetic long position in the call that we created via other financial instruments. Yep. Now let me go to the Excel file to quickly show you guys. Uh, check. So in this dynamic hedging example, you basically like have so you have three tabs: weekly hedging, daily hedging, and hourly hedging. So the intuition are the same. It's just that you are dealing with different frequencies. So I will just walk you guys through weekly hedging. So here for this particular simulation, so we start with data of this value. Like that's the data for shorting your call. Actually, that's calculated like via like the formulas I just showed you guys in the lecture. So but you can forget about that, so you don't have to calculate that. And then like to hedge that data from shorting the call, you would be buying the underlying, right? And in order to calculate the buying of the underlying, oops, I changed the simulation. Anyways, so here for this cell, in order to hedge that, like in order to hedge that data with the shorting of the call, we just calculate like 100,000 times D2, since that shorting of the call option is associated with 100,000 shares. And also we know that for the underlying, the delta is equal to 1. So if we substitute delta equal to 1 and that 100 shares, sorry, 100,000 shares into the portfolio data, we'll get that actually the like the shares in the underlying should be like 100,000 shares times D2 times the delta of the like delta of the call option. Sorry, actually the delta of our short positions in the call. So what I'm trying to say here is that this cell, it's purely just for calculation of the shares in the underlying to reduce the previous cell to 0. Like yeah, that's and then also also here for this, like for this column, we're just calculating the cost of buying shares. So we're just using shares times the stock price. Then for the cumulative cost, it's actually just like, for example, if you look at the like this cell, it's actually just the cost of shares at each period plus a previous cumulative cost and then plus interest cost. And also furthermore for actually for like as we can see for the cumulative cost, we included interest cost. And that interest cost is just the cost we spend in the the cumulative cost we spent in the underlying asset in the spot times the interest rate divided by 52. So the interest cost is reflecting that by investing in the underlying, we are generating some opportunity cost because if we do not invest into that underlying asset, if we invest into other, for example, into savings, we're just going to receive the interest payment. So we're just giving up that interest payment if we invest in the spot. Um, then also one more thing here. So here, so this example for this simulation, like note that once you like click onto each cell, the simulation is going to change. But now for this, like for this example, like for this current simulation we are at, we can see that like at the end of like basically at maturity, which is week 20, the stock price is out of the sorry, the stock price is very low, and therefore the call option we hold, sorry, the short position in our call is so what I'm trying to say is just that the call option is out of the money. So since it's deep out of the money, the delta is actually zero. So yep. And also for the like for the intermediate cells, here, like let me also describe the second row a bit, so you'll get the vibe of this simulation. So for the second row, now the like as time goes by, the delta changes to this amount. Maybe let me change that back. Change to this amount, 0.3607. Then you have to adjust your long position in the underlying, right, to reflect that change in the delta. And to reflect that change, to make the delta of the entire portfolio back to zero again, you would be like deducting your long position in the shares. Therefore, this cell is just like it's just reducing the positions in the shares in the underlying. And since now you are selling the shares, your cost of shares purchasing would be negative, reflecting that you are receiving money from selling shares. Yeah, that's pretty much the simulation here. But you guys can see that our total hedging cost, so total hedging cost, like the cumulative cost, is very close to the selling price of our call for each of the simulation. So this Excel is just actually an illustration of this bullet point here. You can also play with this daily hedging tab and hourly hedging tab, but the logic is the same. So and also you can check the total hedging cost with our selling price of the call option. They should be really close to each other, like for each of the tab. Now let me get back to the slides. Uh-oh. Also one more thing here. So remember that like on the let me find my pen. So here I only have one more thing to discuss. So remember that actually, so for a forward contract that's paying continuous dividend yield, we know that the like the delta is e to the power of minus qt, right? Since for forward contract not paying dividend, sorry, for forward contract on underlying asset not paying dividend yield at all, that q is equal to 0. Therefore, it's equal to 1 for q equal to 0. So since we have delta of forward being 1, if the underlying has no dividend yield, and to hedge that like to hedge that forward contract, we would be like if we want to hedge our short position in a forward contract, we would just be longing one longing one underlying, longing one share of the stock and shorting the one forward. And since for both a forward contract that we are shorting, and also for the hedge we use, which is the stock, like for both of them, their delta are constant, are being one. Therefore, such a hedging portfolio does not require like regular rebalancing. So with forward contracts, if we don't have dividend yield on the underlying, we can just hedge and forget. Yeah, that's all for today. Thank you guys for attending this lecture. Bye.